So as an introduction to the topic of multirate signal processing, we can consider the example of the digital audio tape and the audio CD. So the digital audio tape, or at least the consumer variant of it, was sampled at 48 kHz, while CDs are sampled at 44.1 kHz. So if you have a song stored on a DAT tape and you want to transfer that to a CD, the song somehow needs to be resampled in order to fit the new format. And conversely, if you have a song on a CD that you wish to move to a DAT tape, it also has to be resampled. So a similar situation is faced with images. So if you have a device like a camera which captures an image, the sensor in that camera will have a certain number of pixels in order to capture the image. However, the screen or the several screens on which you want to display the picture in the end will have a different number of pixels. So the image captured by the sensor somehow needs to be resampled before it's displayed on the screen in order to match the pixels on that screen. So let's consider an example to see what would happen if we did not resample the picture. So suppose that you have a digital audio tape with a song sampled at 48 kHz, and you were to move those samples sample by sample onto a CD, which assumes a sample rate of 44.1 kHz, and then you were able to replay the CD at normal speeds. So what do you think the sound or the CD would sound like? Would voices and music have a high pitch and sound like chipmunks? Or would the voices have a low pitch and sound like ogres? Well, the correct answer is option number 2. So one way of coming to this conclusion is to note that at 48 kHz, the DAT tape will typically have more samples than the CD. So if we were to put those samples on the CD and replay, the song would get longer, so it would be stretched to a longer period in time, and therefore the pitch would be lower, and voices would sound slower and with a lower pitch. So multirate signal processing refers to systems that operate on 2 or more sample rates within the same systems. So the topic of multirate digital signal processing from the point of view of the course would be, how do we change the sample rate of a signal? So how do we go about it practically? And also to understand, and these two go together, how a signal is affected both in time and frequency when we do change the sample rate. So a useful tool when thinking about rate changes for digital signal is to look at the analog of time continuous signals, where we can simply stretch signals in time while multiplying the time variable by a constant. And that also gives us a relation for what should happen in the frequency domain. So we know that if we have a signal x and we create a new signal y of t, which is simply x of a constant times a time variable, that affects the Fourier transform in the following way: that the Fourier transform of the new signal is simply the Fourier transform of the old signal scaled in amplitude by 1 over c and also in frequency as 1 over c. And this is what we saw in the previous question as well, that if we increase the length of a song, we will typically reduce the pitch of the song, while if we decrease the length with a c smaller than 1, we will increase the pitch by increasing the frequencies. However, if we look at digital signals, we realize that a similar expression cannot hold unaltered. And this is because digital signals and their discrete time Fourier transforms have to be periodic with period 1. So if we assume that x of t, or rather its Fourier transform x of f, was periodic with period 1, as soon as we scale it according to this formula, we cannot maintain that periodicity. So instead we would get a periodicity of 1 over c. And this cannot happen, of course, in the digital domain. So we need to break off from this formula, but still we wish to strive to have something similar in the digital domain. So just to illustrate the challenges involved. So here we have a digital signal consisting of 10 samples in this case. And suppose now that we wish to double the sample rate. So essentially over the same range of time, we want to have samples from 0 to 20 or 21 samples in this case. So the problem that we face now is that we have a bunch of positions where we are lacking samples, and we need somehow to fill them in, right? And one way of thinking of how to fill these in optimally is to assume that these are samples of some underlying waveform. And that of course tells us immediately how to fill in the missing samples, so we simply pick them from the same waveform. Now, the only trouble with this way of thinking is that this gray line here is not the only waveform which passes through the sample points which we had to begin with. So you can, for instance, pick another waveform which also passes through those. And if you chose your sample points to fill in from this new waveform, you get a different solution. And we need to argue about which of these solutions would be the best one. So one way of guiding us would be to move into continuous time. So we know that if we have a sample signal, which is or a discrete time signal which is sampled appropriately, then we can recreate the continuous time signal through a process called pulse amplitude modulation. So in principle, what we could do when we change the rate of a digital signal would be to take this digital signal, move into the analog domain by pulse amplitude modulation, and then resample at the new sample rate, and that would give us a new signal. And you can express this in terms of the pulse amplitude modulated waveform, like such, and get the new signal. However, moving into the continuous time domain within a digital system would hardly be practical. So what we will look at are ways of trying to do this purely in the digital domain. So a question related to this concept of sampling, which will be useful also in what follows. So suppose that we have a band-limited continuous time signal x of t, which has a Fourier transform which is identically equal to 0 outside of this band of frequencies. Then what is the slowest sample rate with which we can sample x of t so that we will be able to recover the original continuous time waveform from the set of samples in the end? So is the smallest sample rate 1/2 of the bandwidth? Is it equal to the bandwidth, or is it 2 times the bandwidth, or none of the above? Well, the correct answer is option number 3. We always need to sample at 2 times the bandwidth of the signal if we wish to be able to recreate it. And 2 times the bandwidth is typically referred to as the Nyquist frequency. So we have to sample at least the Nyquist frequency in order to be able to recover the signal in the continuous time domain. And this is referred to as the sampling theorem. So just a summary from the introduction. So we need rate conversion in order to change between different storage. And rate conversion can also be used as a technique in many different signal processing methods, and we'll look at that in the next lecture primarily. It has a strong relation to the concepts of sampling. It will have a strong relation to the concept of aliasing, which appears in sampling, and also to the concept of pulse amplitude modulation, which we just saw an example of.